than we normally do. That's okay, whatever, it is what it is. Maybe there's a big test or something coming up. All right, so let's start with this one. Give me a second, I'll get the polls going. Oops, we do not. Yes, want you all to be able to see what the TAs are saying to me. All right, let me get the polls going here. All right, there we go. So this one shouldn't be too bad, right? There's like no computation that needs to be done. You just basically start, you look at the graph and you tell me, where is the derivative equal to 0? Okay, so we're not going to spend too long on this one. Again, it's basically just inspection. Okay, sure, yeah. I mean, like, I'm happy, we'll definitely talk about this. But just think about, like, geometrically, what does the derivative represent, right? Like, and if you know that, then it should come pretty quick. And if you don't know that, then we'll cover it. Okay, so I'm going to wrap it up in 30 seconds. Where's my pen? There it is. Okay, so this is actually pretty critical to understand because this is really going to come up and affect us later. So the class is leaning towards A, which is great, but there are a good number of people in the BCD camp, which is we need to try and fix, because like I said, this is kind of an important concept later. So I have copied the graph here. So I'm just going to paste this in, make this a little bit bigger. Okay, what is the derivative geometrically? How can we think about it in terms of the graph? Does anyone have an idea? Right. Okay. Yeah. So it's the slope of the tangent to the graph, right? So it's the slope of the tangent. So recall that f prime of x is the slope of the tangent line at x, right? Okay, so let's choose a point and let's see what that might look like. So let's say I chose the point, ooh, that's a weird color. I thought I selected green. Why is it not selecting green for me? Okay, this is very weird. Here, let me kill OneNote and we'll just restart it and hopefully that will fix it. If it's not the pen, then it's OneNote itself. I'm just blaming Microsoft for everything. Okay, let's see if this works. Can I? Look there, now it works. And IT 101, everyone. If it doesn't work, turn it off and turn it back on again, right? Okay, so let's look at what happens when x is equal to 1. So what that says is you would go up, you would find that point on the graph and you would draw the tangent line. So obviously I'm not going to draw a great tangent line because I'm not. Oh, look at that. It's so squiggly. Whatever. It is what it is. Okay. And so this tangent line here, right? The slope of that thing is f prime of x. Right? Or if we chose a slightly different point, maybe we could choose, I don't know, let's choose negative 1.5 here. If we came down, and again, I'm going to try to draw the tangent line like this. Okay, that slope is f prime of like negative 1.5. I guess I can actually say what this is. This is f prime of 1. Okay, so the derivative is the slope of the tangent. So if I'm asking you, so the question said, determine where f prime of x is equal to 0, right? So where is f prime of x equal to 0? What are we asking, right? Like, what kind of line has that slope? Yeah, exactly. A horizontal line, right? Does everyone agree, right? Like the horizontal line is the line with slope 0. So what we're going to do here, let me erase these pink and green things. So what we're doing is we're looking at this graph and we're trying to find, by just visual inspection, which places are going to have a slope of 0. And if you look, it looks to me like probably here, has a horizontal slope. And about here has a horizontal slope. And then about, here has a horizontal slope as well, right? So what is that? That is x equals -1, 2, and 3. And I believe that that was answer A. Hopefully. Yeah, it looks right to me. So does that make sense? Are there any questions about that? Okay, what specifically seems to, which part? Yeah, try and pinpoint those. So the slope is the derivative is the slope of the tangent line, right? Okay, and the slope of 0 is horizontal. Is that okay? Okay, so if you looked at these, like, you have to try and visualize, the slopes of the tangent lines. So if you pick a point, draw a tangent line, pick a point, draw a tangent line, pick a point, draw a tangent line, right? And if you just kept doing this, and hopefully you can kind of visualize what's happening as you move this point around, and the slope of the tangent line, it just kind of moves around with it. You're looking for the places where the line is horizontal, right? And so what you hopefully see is that they tend to happen first at local maxima or minima. And this is actually going to be important in a little bit. Basically, they happen, if this is a roller coaster ride, they happen right at the bottom of the roller coaster and then at the very peak of a roller coaster, right? So the horizontal lines, you're going down the roller coaster, whee, and then you hit the bottom, boom, your slope is horizontal there, and you start to climb back up. And then just as you're about to start falling again, you've got a horizontal line and that sort of thing. So does that make sense? So the points that you're interested in are this point, and that point right there. Okay, and like I said, this is going to be important when we talk about maxima and minima later, because we're going to learn that if you're a maximum or minimum, so you're smaller than everything nearby or you're bigger than everything nearby, that really does correspond to a place where your derivative is equal to 0. And we're going to give these things special names. They're going to be called critical points. And so when we're trying to find maxima and minima of functions, one of the ways that we're going to do that is we're going to do critical points, right? We're going to use critical points. So that's something to keep in mind there. And yeah, that's just what it looks like on the graph. And again, we kind of, if you look at the graph, you can see that they correspond to maxima and minima as well. Okay. Ooh, I like this one. Let's try that one. And I think actually we graphed this in office hours on Tuesday. I think somebody brought this question up, right? So those of you who were there in office hours might have a bit of an advantage with this. Mhm. Same, strictly speaking, no, it was not. So the limit laws are only those exact four that we talked about. That I would say is a property of continuity. Yeah. Yeah, but I mean, it's pedantics, right? It's just like, what do we call them? So in some sense, oh, for sure you can use it on the assignment. Yeah. I mean, like, again, in a sense, if you wanted to call it a limit law, you can, but if in doubt, you can just quickly explain it. You'd be like, oh, I'm going to use the fact that since the function is continuous, I can take the limit inside of it or something, right? So if you're ever not certain what to call it, you could just describe it roughly. I'm going to close down in 30 seconds, everyone. No, yeah, if it's not continuous, you can't take the limit inside, right? That's a special property of continuity. Group type, sure. I think we did some on Tuesday though, but we can take a look at it. Okay, let's stop this. All right, so the class, so majority of the class said B, which is great because B is the correct answer. A good number of people said D though, and that was specifically what this question was designed to do, is D was the primary distractor that we expected to get a bunch of you with. And because I think the reason for that is we know the absolute value of X is not differentiable at 0, right? But that's not what this question is asking, right? This question isn't saying, is the absolute value of X differentiable at 0? It's saying, is X times the absolute value of X differentiable at 0? And it turns out the answer is yes, absolutely it is. And the answer is 0. Okay, so there's a couple of ways that we could do this one. One is just using the definition. So, without graphing it, I did, yes, that was my goal. I was trying to trick you, because better to trick you now than to trick you later, right? I'd rather trick you now than trick you on a test. So let's just, once I show you the graph, I think it won't be too bad. But if any of you are interested, pull up Desmos and plug in X times the absolute value of X and take a look at what this function actually looks like. And you'll see, right, the reason why the absolute value fails to be differentiable is it has this corner, right, at 0. It makes a very quick and radical change in its direction. And yet X times the absolute value of X does not have that, right? And I'll show you again how you could have guessed this in a second. But for the moment, let's just do it algebraically, right? Let's pretend that we didn't have access to fancy graphing equipment and we just wanted to do it like that. Okay, so we've got f of X equals X times the absolute value of X. Okay, and of course we know that f prime of 0 is the limit, right? We're gonna, just really ingrain this into our heads. The limit definition of the derivative, like this, right? And of course, 0 plus h is just h. And hopefully you all agree f of 0 is 0, right? If you plug 0 into this function, you just get 0 out. So this is going to be h times the absolute value of h divided by h. Does everyone agree with that? Like that limit works out like that? Okay. Now the h's cancel, right? So boop, boop, those disappear. We get the limit as h goes to 0 of the absolute value of h. That function is continuous, right? So we can just plug h equals 0 into that, and boom, we're done, right? How do I go from one step to another? So this is the definition, right? And this is me plugging everything in. Right? So f of 0, this thing here, that's equal to 0. This thing here is h times the absolute value of h. Yeah. Okay, cool. So, right, if in doubt, don't just guess, right? If in doubt, actually work out the mathematics. And what we get here is, yeah, we get a number. So it exists, right? F prime of 0 is equal to 0, just because we can go and compute it. Now, if you're curious about what this function actually looks like, let's try and think about what the graph of this thing looks like. Like, how would you actually do this yourself? Well, we know that the absolute value of x is this thing, right? Always, always, always use this when you're dealing with an absolute value, right? How come I know? Well, so we know that the absolute value of h is continuous, or really the absolute, like, it doesn't matter if I call this h or x, right? Like, would you agree with this? Or is it really the absolute value of x that's bugging you? Right? Because the x there is just a dummy variable. So if we replaced it with an h, it's the same thing, right? The x isn't actually important. Yeah, the function is continuous. Yeah. Or the absolute value function is continuous. Sure. I mean, like, you generally have to check that a function is continuous by evaluating the limit. You kind of don't have a choice in that. So I was asked, how is f of 0 plus h, h times the absolute value of h? Okay, so this is f of x. So 0 plus h is just h, right? So if I plug h everywhere I find x, I get h times the absolute value of h, right? It's the same function, it's just got h in it. Yeah. Okay. And like, again, so the graph, so from this point here, you know what the absolute value looks like, right? It's like this. And there's no holes or anything in this function. Like, you can totally just evaluate that limit by plugging in 0, right? Okay, so again, does Desmos work better to find the answer? Well, you can't appeal to Desmos in your solutions, right? So you need to be able to do it. What if x was a number other than 0? Well, actually, in that case, the answer becomes even easier. So here, this graph question will actually help us answer that. But that's a great question. Like, what if we weren't looking at 0? How would we do this? The answer is actually to figure out what this function looks like as a piecewise function. So I think something that will help everyone is when you see an absolute value, I think most of you kind of have internalized this as, if it's positive, drop it, like just drop the absolute values. And if it's negative, get rid of the minus sign. And instead, you should sort of think of the absolute value as being a fancy notation for this piecewise function. Okay, so that's all the absolute value is. It's just a fancy way of writing this piecewise function down. So if we look at x times the absolute value of x, what I'm just going to do is multiply everything here by x. So that will give me x squared if x is greater than or equal to 0, and negative x squared if x is less than 0, right? Does that make sense? And I got know as a general rule, like, you can't solve things just by looking at the graph. And so looking at the graph is not a valid solution. Like, Octave doing the math for you, like doing the computation for you, is one thing. But saying I looked at the graph on a question where you can actually do the algebra isn't sufficient, just because the graph could be lying to you. Like, I can create questions where Desmos will give you the wrong graph. Mm-hmm. Okay, so does this make sense, everyone? That this is if I wanted to get rid of the absolute value and write f of x in a piecewise form, so I just multiplied everything by x, right? Look at, right? This thing is this thing. So multiply everything inside of there by x. All right, so I multiplied this thing by x. It gives me x squared. Multiplied this thing by x. I got negative x squared. Yeah, the absolute value of x squared is always positive. Yeah, that's true. Okay, and so now if we graph this, and again, if you plug this into Desmos, you should get the same thing. So if I graph this, so it looks like x squared if x is greater than or equal to 0, right? And then it looks like negative x squared if x is less than 0, right? So it looks like this. Okay, and again, we can see here at this point at 0, if we were to draw that tangent line, yeah, that looks horizontal, right? That's sort of the idea there. If you were to graph it, why this one actually works out. Okay, now Saeem asked this excellent question, which is what would happen if we were asking this question at some other point, like if we weren't asking about this question at 0. So for example, what is f prime of 3, or something like that, right? Well, when we're looking at 3, we don't care about what's happening when x is less than 0, right? Like we don't care about any of that. When x is 3, we are very, very much only dealing with x squared where x is greater than 0. So that's the same thing as saying is the same as what is the derivative of x squared at 3, right? And what's the answer to that? What's the derivative of x squared at 3? 6, exactly. Okay. So are there any more questions about that? Is everyone all right? This entire point of this question is to freak you out with the absolute value. But again, the absolute value is really not a restriction in this problem. I suspect that if we gave you, this version of f to begin with, many of you probably could have done this. But the absolute value is put there specifically just to kind of freak you out, right? So the idea is if you got something like that in a test, don't freak out. You know what the definition of the absolute value is. It's in the notes many times. And just use that in order to help facilitate and figure out what the answer should be. Okay? All right. I don't hear any major objections. Okay, yeah, sure. That's a fair question. So the question was, how did we get 6? So this kind of, I don't remember which example I did in the notes. We're definitely using here the fact that we've computed x squared at some point in the past, either in the book or in the videos or whatever the case is. But here we can do it really quickly. So let's say g of x is x squared, just so we don't confuse it with f, right? Let's just compute g prime of x in general. Minus g of x, right? So I would only need to do this at 3, but let's do it in general. In this case, unlike the rational question that we did earlier, it isn't actually that much more work. So this is going to be x plus h squared minus x squared divided by h. Okay, and I'm going to skip some steps here because this isn't the problem that we're actually working on. But if you work this out, you get 2xh plus h squared divided by h. Certainly the h's cancel. H goes to 0. So we're going to get 2x plus h. And if we plug h equals 0 into that, we just get 2x, right? So this tells us the derivative of x squared is 2x. So in particular, g prime of 3 is 2 times 3, and that's equal to 6, right? So that's where the 6 comes from. So what we're doing there, it's not the sort of thing that you should have just been able to guess. We're relying on the fact that at some point, again, either in the videos, I don't remember if I did this one in the video, so somebody remind me if I did, but either in the videos or in the PD, like in the book, this computation has been done for sure. How do you get 2xh? So expand out the x plus h squared, right? Like actually just try to do this computation and see if you can work it out. But yeah, actually do expand out x plus h squared, subtract x squared, and you'll see the 2xh come out. Couldn't I have done the product rule and did 2 times x times, well, just x times x. But yeah, you could totally do the product rule that way if you want. It's just a little weird to use the product rule on x squared. I mean, you totally can. It's just that, like, if you have the product rule, you probably have the power rule. And then if you have the power rule, like, you might as well just use it, sort of thing. But yeah, absolutely, you could use the product rule. And yeah, you totally get the right answer as well. Yeah. Yeah, that's one of the great things. And I mean, for those of you who don't know what these are your next week's readings, right? Like the power rule, the product rule, quotient rule and stuff. And some people already know about these because they've already done some calculus. But one of the great things about, calculus and mathematics and how it works is that as long as you apply the correct tools, you'll always get the same correct answer. And there's a bunch of different ways you could do it, but they all arrive at the same thing, right? So the derivative is always using that H formula for now. Yeah. I mean, there's another definition of the derivative, right? So we could have done as well. G prime of X is like the limit as Y approaches X, G of Y minus G of X divided by Y minus X, right? So this is in the videos for sure. This is, I think the video is called like an alternative definition of the derivative or something. You could use that instead, but definitely for like this week, almost all of our derivative calculations have to be done by using the limit definition of the derivative because we haven't developed more sophisticated laws like the product rule and the quotient rule and these things. That's next week. But once we have those next week, we'll be able to use them, right? So some people are kind of cheating and they knew what the derivative of X squared was because they knew what those rules were. But for us right now, strictly speaking, we have to use the limit. Okay. All right, let's, here's another quick one. Ooh, wait. Oh yeah, no, we're doing that one. Yeah, I'm not skipping that one. Okay, and for the record here, you actually don't need to know what the function is. Uh-oh. Oh, gross. Okay, so you don't need to know what the function is. You can just look at the graph and get your answer that way. Okay, 30 seconds. All right. So this one definitely caught a couple of people. We're split between B and C. B and C are actually pretty close, so we're leaning a little bit more in the B direction. B is correct. Okay, B is absolutely the correct answer. F prime of 0 does not exist here. This one's a little bit tricky. Here, let me again, let's copy this in. Okay, so here's our graph. This one is question 6. Maybe let me just write that in. Okay, so there were a bunch of options, right? There is no tangent line. There are multiple tangent lines. Neither of those is correct. So the answer really came down to B or C. So there's a tangent line, but it's vertical, and so it doesn't exist, or there is a tangent line, so the derivative exists. In both of these cases, everyone, those of you who chose B and C are correct. There is a tangent line, right? The tangent line here is this one, right? I think we can probably guess that, right? It's this line. But what is the slope of this line? So this function has a tangent at 0, but right, it's undefined, right? Like it's vertical, right? There's a vertical line doesn't have a slope because it could be like negative infinity or positive infinity, right? So we just say it's undefined. But vertical lines don't have a well-defined slope, right? So f prime of 0 does not exist. Now, you didn't have to use the definition of the function, but if you weren't certain, right? Because you'd say, wait a second, there is a tangent line. It seems like the function should be differentiable. If you weren't certain, you could use the definition of the derivative in order to help you figure this out. So I have a question, how do I know whether it's vertical or horizontal? So remember, horizontal means like left to right, and vertical means up and down, right? And so again, the tangent line here is going to be the thing that kind of like is traveling in the same direction. And at 0, you can see hopefully this function is traveling like straight up, right? And that's how you know that it's vertical. Because in this case, a horizontal tangent would look like this. And that's not, right? That's not how tangent lines work, right? It's not traveling in the same direction. That's actually traveling orthogonally to the curve, right? So in this case, it would be vertical. But anyway, you can actually compute this if you want. So here, let me just rewrite down the function for you. I mean, this looks terrifying, right? Like this is a little bit scary. That's why we gave you the graph. Oops, sorry, x less greater than equals 0. X less than 0. And again, if you wanted to, you could actually compute what f prime of 0 is. We're actually going to have to compute the one-sided limits here. And if we do that, so as we approach 0 from the right, we're in this regime. So we get the square root of h divided by h. That's the limit as h goes to 0, 1 over root h, and that doesn't exist. And so we'd be done even just from this one-sided, but if you wanted to do the other side, it would be the same sort of thing. If we did the limit as h approaches 0 from the left, that's the limit as h approaches 0 from the left. Okay, so now we're in the bottom thing, right? Now we're in here. So we get negative root negative h divided by h. That one's a little bit trickier, but we would get the limit as h goes to 0 from the left of the negative square root. Well, I guess we could do it negative 1 over root h, and that also does not exist. Right? So either way, you would only need to do one of these, but if you wanted to do this algebraically, if you actually start to do this computation, same sort of story, you actually get something where the derivative does not exist because it's in some sense it's infinity, right? Okay. Is there, and here's another example that you can do. If this one's a little bit weird, you're like, wait a second, this is a weird piecewise function. If you want to do a different one, you could take the cubed root function, right? So the cubed root of x, when you graph this thing, it looks like this. Okay, so it looks actually very similar to that other graph, right? So this is y is equal to the cubed root of x. And you get that same problem that at 0, you get this vertical tangent line, right? Same sort of problem. And again, if you actually do the limit definition of the derivative on this, we called it g. That's the limit as h goes to 0 of the cubed root of h over h. That's the limit as h goes to 0, 1 over h to the 2/3. And yeah, that thing again does not exist, right? Because it's like 1 over something that goes to 0, right? So that does not exist. Okay. 511, 513e here. Let me just write those down. Okay, is everyone good there? Does that make sense? Like, how do you determine if a tangent line is vertical or horizontal? So it all comes down to the definition of a tangent line, which unfortunately is a little bit nebulous. But basically, the tangent line represents, there's a bunch of like silly ways that they define it in high school. What do they say in high school? It's like the line that's traveling in this, that intersects the curve only at one point nearby and is traveling in the same direction or something along these lines. But basically what I want you to do is I want you to pretend that you're like driving in a car. Okay, so you're driving in a car and you're following the path, right? Yeah, but so touches at a point once is kind of a freaky definition, because like, what if this is your, no, that's not a function. So if I gave you something like this, right, your tangent line, I haven't drawn this very well, but can actually intersect your curve multiple times. So you have to be careful about that. What you want is that it actually only touches your curve once nearby, if that makes sense, right? But here's what I want you to do. So what I want you to do is pretend that you're driving in a car and you're tracking like, what your headlights are looking at. So at any given point, the tangent line is your like headlight beam, right? So if you're standing here, like what are your headlights doing? Oh, they're pointing in this direction, and we're just going to make it point in the other direction for the sake of it. And if your car is here, which direction is your headlights pointing? Oh, it's pointing like this. Okay, so the tangent line are your headlights, right? And taillights if you want. They're the direction that those things are pointing. So when you get to 0 here, right, when you get to this point at the origin, which direction are your headlights pointing? Well, they're pointing straight up and down. Does that make sense? Right? And it's just for a single instant, right? There's just a single moment where your car is pointing straight up in terms of its headlights, but it's pointing straight up, and then your headlights start to point in a different way. Okay, and vertical is where your headlights are pointing up and down, and horizontal is where they're pointing side to side. Yeah, no problem. So again, there's this, oh, your function touches, or your tangent line touches your function only once. Again, strictly speaking, that's not true. Right? Again, here's one. Here's your tangent line. Well, oh, it hit there again, right? So you have to be a little bit more careful than that. But whatever, it's high school. And also, what about this? That also touches the function only once, right? But it's not a tangent line. So you know what I mean? Like, we have to be careful about using that definition of tangent. But you can see here, if you're using the headlights on a car idea, there's no way your headlights are pointing up and down at this point, right? Like, your headlights are pointing like this, and then like this, and then like this, and then they start to point down, right? And so that's, I think the headlight analogy might be a better way of thinking about that. Okay, so let's do, I don't want to do that one. That one's boring. All right, here, this one's very similar to, I think, the first question that we did. Let's see if we can get this one. So it's a little bit different though. Previously, we were asking for, we gave you a graph and we said determine where the tangent lines are horizontal. Now what we're asking you for, which of these functions is the derivative at 2 greater than 0? Okay, and it's the exact same sort of thing, right? It's the same sort of question. Nice. Okay, 30 seconds. Class is doing really great. I love it. And again, I should probably just copy the graphs. All right. Yeah, this is great. This is what I love to see. Good job, class. Like 78, 80, basically 80% of the class said A. A is absolutely the correct answer. We'll do this one really, really quickly, just so I can, because I suspect some of you might want to see a slightly more challenging question. I do have one primed up. I've actually got two primed up, but let's try and give you one. So very quickly, if we just draw the tangent lines. So here's 2, and we draw the tangent line. Okay, so I'm just going to do this quickly for every single graph. So we get something like that. We get something like that. And for here, we get something like this. Okay, and the question asks you for which value is f prime of 2 greater than 0, i.e. which of these lines has a positive slope, right? And so for a positive slope, right, like when you compute rise over run, the only one of these, so B has slope 0, right? So this is slope 0. This slope is negative. This slope is negative. This slope is positive. So this is your answer. That's good. Okay. Let me give you a okay, you know what? Maybe I'll let you choose which one you want to do. All right. So can I zoom out like this? Okay, kind of. Okay, here are the 2 questions. You tell me which one of these is more interesting for you. In fact, why don't we vote on it? We'll vote on it as a poll. Okay, so A is the first question, B is the second question. Good, couple of C's and D's in there. Good, always enjoy the anarchy. Appreciate that. Wow, this is surprisingly split.
Yeah, it's very close right now.
Just when you think one is getting ahead, the other one catches up. Okay, let me say 10 seconds. Get your votes in if you have an opinion. A couple protest votes in there.
I mean, currently one has a slight majority over the other.
Yeah. All right. Yeah. So people want A, and if we really want to, yeah, we can do them both. Absolutely. We're going to have to run into office hours, but I know you're all technically free because those aren't actually that's actually part of the lecture. I'm pretty sure, right? Our Thursday second hour is actually part of the lecture. So yeah, we can do them both. So, all right, first one first. Oh, okay, right. This really does not like me using the touch feature for it. Okay, so that's our first one. Let me restart the polls here. And you can see, right? No access to Desmos or Wolfram Alpha is going to help you do this question. You either know what you're doing or you don't.
I got that a few times today in the tutorial, whether they can use Desmos or not, and I told them it doesn't matter. You can, if you want to double check your work, but it's not really going to be very prevalent when you're actually trying to answer the question.
Yeah, same thing. Like if we ask you what's the derivative at 0 and you say by Desmos, I graphed it and I got 0. Again, remember everyone, that doesn't actually count because it's not doing a computation for you. Desmos is just doing an approximation, right? And it's actually, again, it's very possible for us to give you something that looks like it has a horizontal tangent, but doesn't. So you have to be really careful with these things.
Mhm.
So Ahmed, what I'd suggest trying to do as a start is writing out what the, you know that f prime of 3 is equal to 8. We'll write that out as a limit definition and see if you see anything familiar. Yeah, I'm sure. All right, nice. Looks like a lot of people are getting the right answer. That's awesome. True, true. Okay, I'm gonna call it here, let's say 40 seconds. So far though, 80% of the class has this right. 80% of those who have said, given an answer have it right. So that's pretty cool. All right, 5 seconds. Yeah, sure. All right, so yes, 70% said C. C is absolutely the correct answer. Good job. And again, maybe some of you got it from guessing. Maybe some of you got it legitimately. That's phenomenal either way. But let's see if we can't figure it out, right? So this right here, this is question 9. All right, so what are we told? We're told f prime of 3 is 8, and we're told g prime of 3 is -2. Okay, and we want, so the question is, find the limit as x approaches 3, f of x minus f of 3 divided by g of x minus g of 3. Okay, so the key to this one lies in thinking about what these two limits are, right? So let's write them out. So f prime of 3. And the important point here is to use this version of the limit definition. Like this. Okay. And if we look at this, we see a couple of things, right? So note that this thing right here is that. This thing right here is that. And the only thing that we're missing, right? In the limit that we're trying to compute, the only thing that we're missing is the x minus 3's, but it's common to both of these things, right? Like there's an x minus 3 in the denominator here, and there's an x minus 3 in the denominator here, right? So what we're going to do is when I'm trying to compute this limit, okay, what I'm going to say to myself is, well, I have no idea what this limit is, right? Like just absolutely no clue. But I do know what this limit is. So it would be really great if I could make the x minus 3 somehow appear so that I could use this, right? So what I'm going to do is I'm just going to force it to appear, right? I'm going to multiply top and bottom, like I'm just multiplying by 1 here, right? So I haven't changed the limit at all. And then I'm going to write this in a good way, right? Let me maybe split that up like this. Right? And lo and behold, that's that one, right? And this is this one, only upside down. But that's okay, because we know how to take reciprocals of limits, right? Like this is one of the limit laws. And so what I get out of this, by the limit laws, both of these exist, and this will be f prime of 3 times 1 over g prime of 3. That's 8 times 1 over -2. So the answer is -4. Does that make sense? The last step again, sure. So here, probably the important part is the 1 over g prime of 3. I think that's probably the part that is messing people up. So everyone, I think, is okay. Is everyone okay with the fact that this is f prime of 3? Right? Right. Yeah, like I figured, it's the 1 over g prime of 3 that's probably bugging people. So everyone's good though, right? That part's f prime of 3. How do we get a denominator? So I used this one as the denominator for this, and then I used this one as the denominator for that. Why did we multiply by x minus 3? Because I want to be able to use this fact, right? And in order to be able to use the fact that I know what this limit is, I need there to be an x minus 3 there. And there was no x minus 3 in my original limit, so you force it to appear. Okay, so the 1 over g prime, let's just think about, it might actually help to kind of do this backwards. So let's think about what is 1 over, what's the best way to say this? Here, yeah, let's compute the limit as x approaches 3 of x minus 3 divided by g of x minus g of 3. Okay, that's the same thing as the limit as x approaches 3 of, and you know, this is kind of gross when we write it like this, but perfectly legitimate, right? So if I take 1 over a fraction, it's the same as flipping that fraction upside down. So these two things are equal. Is everyone okay with that? Yeah, that's okay. I'm going to assume unless anyone yells. Okay. And we know that right by the limit laws, we know that the denominator exists and is not 0. So by the limit laws, I can take the limit of these two portions, but the limit at the top is obviously just itself, right? And that's exactly g prime of 3, right? Well, I didn't say these were the easy, I said these were the challenging questions, right, Sylvia? So I mean, that's okay to an extent. But yeah, the key is to recognize that these things look like derivatives, but how do we make the derivatives appear? Okay, there's a little bit of a trick to it, right? But that sort of thing, multiplying by 1 or adding a 0, these sorts of things, you know, come up, and they are valid tricks. They're not typically the tricks that I probably would ask you on a test. I think that this, you know, asking these sorts of questions on a test is mean because it doesn't actually test whether you understand derivatives. It tests whether, how good of a problem solver you are, but that's not necessarily what I'm trying to test, right? So for the first step, how did we apply the definition of a limit to arrive at, so this is like we were told, right? So the question tells you that f prime of 3 is equal to 8. And so I just wrote down what that means, right? Like, see, Aziz, the f prime thing is just, right? Like that's just shorthand for the limit. Is there another math course where this type of problem solving appears? Like all future math courses? So if you went and did more math, that would definitely happen. In terms of like, the reality is this shows up anywhere. So even for those of you who have to do stats, this sort of thing is going to show up there as well. If you're interested though in seeing this sort of stuff, taking the proofs course would be a good place. I know most of you are probably like, no, I'm just doing this math and I never want to touch math again. That's fine. But yeah, if you're interested in this, 102 would probably be a good place to start as well. Yeah. Yeah. I just mentioned Math 102. So that's the courses in the department's Intro to Proofs course. But like I said, this sort of stuff shows up in a stats course as well, like where you add and subtract zeros. Proofs are a whole different beast. Proofs are real math. So nothing that you've learned in high school or frankly in this class is what most mathematicians would consider real math. Math 102 is the first place where you would actually see real math. And it's, it's tough because most students have never done that math before, but like, Jeremiah, that's totally fair. Totally fair. Yeah. Okay, yeah, let me do, so a couple of people asked for, like, we're into office hours now. So a couple of people asked for some 5-11, 5-13. Yeah, no, I don't think that that's true. That might have been true at one point, but it's not true anymore. So I got a direct message saying, so basically Math 133 is a bird course. And I don't think that that's true, okay? Shanze, I don't know what question that is. Oh yeah, question 10. Yeah, here, let me post it up and then I'll talk a little bit. Because some people wanted to do this one, so let me just post it here and then we can do that. Right, so I think in the past it might have been birdier, like, yeah, so probably like 10 years ago, no, so I think 10 years ago it was, again, it wasn't a bird course, like averages still weren't great. It was more like high school math though, right? And I think you all agree this class isn't like what you've done in high school, right? It's a little bit different. We don't just ask you to memorize recipes and then regurgitate them. Yeah, Davin, that's the fact that there are no trig functions definitely makes it easier. That's true, right? So anyway, back in the day, it was very much just continuation of high school math. And it was here, memorize these formulas and plug numbers into these formulas, right? So that's how that course ran. Right, exactly. We're more interested in sort of like, do you understand the concepts? Do you actually understand what you're doing rather than just memorizing stuff? And the reason for that is, and again, right, part of the question is, why do we even make you take this course? Especially if you're going to go be like an accountant, for example, like, why do you care about derivatives, right? Or like for most of the commerce degrees that you guys do, you're not going to be worried about most of this stuff, right? And so part of the answer to that is that it's a weeding course, right? Like I don't like that it's a weeding course, but that's definitely part of it. But part of it as well is to make you a problem solver, right? Is to help expose you to building your abstract thinking and your problem solving and your conceptual understanding and these sorts of things. And recipe mathematics doesn't help you with that at all, right? Because what we would find is in terms of retention, when you do a recipe mathematics course, within 3 weeks of the final exam, everybody's forgotten everything, right? And I think a lot of you know that. Like you've all, I'm certain, because I have too, written an exam and then forgotten everything about that course 3 weeks after the exam happened, right? And some of that might be true for this course as well. But the idea is that if you focus a little bit more on concepts and on just a deeper understanding, rather than just throwing complicated computations at students, you enforce a better understanding and retention of that material lasts a little bit longer. So for example, objectively, the computations that we ask you to do in this class are easier than they were 10 years ago, right? It's sort of this balance. So they didn't ask you to understand, like 10 years ago, there was no conceptual understanding in this class, but the computations were quite difficult because it was all just computation, right? It was, here's a recipe and apply it. And so to compensate, the computations had to be quite difficult. Now in this class, what we've kind of done is we've kind of done this, right? Where we've asked you to do a little bit more conceptual stuff. But as a result of that, like we're not interested in whether you can do complex calculations. So we've made the calculations a fair bit simpler as a result. Sure, yeah, and I mean, conceptual understanding is more difficult, Ahmed, and because it's deeper, it's supposed to be a deeper understanding, right? So that's definitely a thing. And it's definitely still like something that we really have to struggle with, but that's why it's more valuable, right? And it's more valuable because as you begin to refine and hone your abstract thinking and your conceptual thinking and your problem solving skills, right? Those are hard skills to learn. But the idea is that if you pick them up here, even if you're not doing math, this sort of mathematics in second year or third year or fourth year, hopefully you're taking those abstract thinking, those problem solving skills into those courses, right? Which is why I'm not worried if you don't do any linear algebra. Right? Again, I've been told I have to do linear algebra because some of you will need it. And I've been told you have to do differentiation and derivatives because some of you will need it. But as a general rule, if you take linear algebra with me and then never use it again, that doesn't bug me because what I'm hoping that you got from the linear algebra portion of that course is learning how to think and learning how to learn, right? That's the goal. But yeah, I mean, and I think as well, some of you, like nobody likes to be confused, right? But confusion is a key and critical part of learning, right? If you're never confused, it's because you're not being challenged enough. So it's all about like being confused and working hard to overcome that confusion. That is learning, right? And the better you get at that, then the better you'll be able to learn in future courses, period. Is there an alternative for this course? You can take any other math course and replace it with this one, like any of the other first year calcs. So if you took 135, 136, 132, 134, I think would also work because it's basically the same as 135, 136. You could take 137, 157 as well. Any of those would count. Yeah, you could, but I mean, those courses all also exist at St. George. So you could also do 133 at St. George if you wanted. 132 and 135, they are, so conceptually they're similar, but they also ask the hard computational questions. Right? Now, that didn't always used to be true. That's just something that's happening more recently. 135 used to be like, what I just mentioned, 133 was like where conceptual understanding was very low and computational questions were very, very high. And so the computational questions were very difficult. And then objectively, 133 was easier than 135, right? Because 135 also had trigonometry, which immediately makes everything harder. What it changed though is 133 was the first to start to go conceptual. Yeah, it's for sure offered in the summer. Yeah. So 133 started to go conceptual. And I think for a while then it actually came that 133 was, I don't want to say more difficult, but really emphasized different things. Yeah, I see it. I will. Emphasize different things than 135 and 136, but 135, 136 is now also changing to this thing. I have no idea who's teaching in the summer. Yeah. The average for this course, like right now or in general? Okay, sure. So that fear though, like a lot of that fear is about being wrong. I really hope that, especially when it comes to lectures, you're not, afraid to be wrong and confused because, right, that's what the purpose of lectures. Hopefully you can be wrong and confused here. And that way you're not wrong and confused in a test, right? Well, okay, yeah. So then if you're coming to lectures and you're not confused, but then you're confused in tests, then we need to find a way to like nail down where that confusion is happening. We try not to diverge tests too far from the lecture material and the practice questions. I know that some people complain that what we do in the lecture is sometimes comes across as easier as what we do in the tests. The reason for that is the lecture is supposed to be where you're learning it for the first time, and then you develop those skills a little bit more with your assignments and your practice questions and those things. And so it should be lectures in terms of difficulty. Lectures should be easier than tests, but those should be easier than assignments, right? And that's the sort of thing. Yeah, 100%. And you should use any and all resources that you can. So if Khan Academy helps, totally like use that as much as you can, right? Jeremiah, in terms of averages, I don't have the average right now because I don't keep a running tally of it. Generally, assuming that tests are the majority, right? Because each test is 10% and every other, Sylvia, yes. Assuming that each test is 10% and all the assignments are like worth 1%. So one test currently outweighs all the assignments we've done. I mean, the averages on the tests haven't been that bad, right? I think they've been hovering around 6, like the early tests were around 70s and now we're kind of hanging around the 60s. In fact, I could just look up what we've had for tests recently. Yeah, that's 13% total though, right? So that's once we've done all the assignments, right? And we've only done 8 assignments and 3 writing assignments. So we're not like, maybe we're at, right? Oh, so you're saying it's 13% total as of now? So it's about, okay, you're right. So it's about a test, right? So it's about the same as one test. Anyway, but you guys all have access to the averages as well, right? I think you can see that in CrowdMark, right? When you go to results, it tells you what the averages were, right? So term test 1 had a median of like 68.5 and a mean of 68.5 and an average of, or a median of 70. Test 2 had a mean of 60 and a median of 60. That's not unusual for a math class. Test 3, that's the wrong test 3. Test 3, 60, 60. So yeah, I mean, like scores around the 60s don't seem to be uncommon. It does, but I think that's mostly just because of the final, right? Like the final exam is worth 30, I think. Yeah, the final exam is 30% of the mark, right? So yeah, right now the marks are probably around 60s, but for a math class, that's totally fine. That's not weird at all. No, unfortunately, no. Yeah, there aren't any more bonus quizzes. Rafid, you might not have been here when I explained that, but basically the bonus quizzes take a long time to make because they're actually part of like how we are tracking longitudinal changes. Yeah, I mean, there are definitely classes too. There are first year math classes where the final exam is 50 and it's just like, oh my God, right? Like, can you imagine doing 2 full semesters worth of work just for your final exam to be half of your mark? Like, that's brutal, right? So specifically, we tried to put as much weight onto other stuff as possible so that your final exam wasn't backbreaking. However, the university has requirements. I'm not allowed to give you a final exam worth less than 30%. Like, that is a hard and fast rule. I'm not allowed to do that, right? In the past, the averages are all over the place for this course. We have definitely had years where we have finished with like 68, 70%. But we've also had a year, I think 2 years ago, where the average was like 55, like the final average. I don't know what happened that year. It was such a weird year. So 2 years ago, so that was the year we actually went into the pandemic, right, in March. So that year, we didn't do anything different from the previous year. We taught the same material. We taught it the same way. We basically had the same instructors. We didn't change anything. And yet universally, their grades were 20% lower than the year before and the year after them. There was just something about that year where they were like a lemon class. They just really struggled, right? Yeah. Okay. Here, let me take this one then. And then, because a bunch of people are getting anxious about doing some, office hour stuff. So let me just take this one up really quickly. So the answer here, here, let me stop my polls. All right. So class is pretty confused, but people are leaning towards D, like 3, 4, 6, 7. Nice. Yeah, D is absolutely the correct answer. Davin, so yeah, D is the correct answer. And what we want to do is, so we're told, hopefully this kind of looks like the numeracy question, right? So f of xy is f of x times f of y, right? And we're told that f prime of 0 is equal to 1. Okay, so what we're going to do here is we're going to say, we're interested in some sort of information about f prime. So let's look at the limit as h goes to 0, f of x plus h minus f of x all over h. Now I'm going to use this fact, right here. So I'm going to get the limit as h goes to 0, f of x times f of h minus f of x, all divided by h. That's going to be the limit as h goes to 0. Actually, you know what? Let me factor the f of x out, which I can do. So that's going to be f of h minus 1 divided by h. Okay. Now, you all showed in your numeracy assignment that f of 0 is either 0 or 1. But if f of 0 is equal to 0, then it's a constant function. And if it's a constant function, f prime of 0 can't be 1. So what that means is that this thing here is actually f prime of 0. And we recognize this as being precisely f prime of 0. So that thing is 1. And there's our answer. The second step, so which one? So this, like this equals? Okay. So there's a couple of things here. Yeah, okay, let me do it again. Okay, is everyone okay up to here? Yeah, they're brutal for me actually too, Daniel. But yeah, totally. I'll keep recording, so you'll get to see them later. Yeah. All right, have a good night. See you later. Okay, but are people fine up to here? And then I'll explain the next step, because the next one seems to be bugging people. So is everyone okay to hear? Okay. Oh no, Connie. Okay, so this step as well. Okay, so here, look, let me take this equation, and instead of writing y, let me change that to an h. Right? And then I'm just going to go whoop and plug that into this. So do you see it now? Cool. Okay. So now this numerator here has an f of x in both terms, right? So I can, here, let me just do this as an intermediate step. I can factor that f of x out of the numerator. Everyone's good with that? Right, so that's how the f of h minus 1 came about, right? I just factored the f of x out of both of those terms. And then I took the f of x outside the limit. So is everyone good there? Does everyone? Oh, so I just took it out, right? I just went whoop, like this and took it out. Because the limit is in terms of the variable h, right? The variable for this limit is h, not x. So that number is just a constant. It's like the number 7 or something. So I can just move it and take it outside of the limit, right? So I plopped it outside of the limit, and then I got, right? So now I'm left with this thing. So in your numeracy assignment, you showed that any function which satisfies this property, f of 0 is equals to 1 or 0. Does everyone remember that? In the numeracy assignment, you were told determine the possible values of f of 0, and hopefully you found that the values were either 1 or 0. Okay, but the thing is, if f of 0 is 0, then that means that f of x is f of x plus 0 is f of x times f of 0 is f of x times 0 is equal to 0, i.e. f is the 0 function. Right? It's constantly just 0. So if f of 0 is 0, then it's constantly 0. How do we know it's 0 or 1? You prove that in the, like, that was your numeracy assignment. That was question 3.1 of the assignment 7. Right? Am I misremembering that? I'm pretty sure it was assignment 7, 3.1. Somebody tell me if I made a mistake there. Okay. But anyway, I'm pretty sure it's assignment 7, 3.1. So if you go and you look at the solutions to that, you'll see how we come up with that answer. Anyway, if f of 0 is 0, then f is the 0 function. And in that case, f prime of 0 is equal to 0. And we said in part of the question that f prime of 0 had to be 1. So that means that this is not possible. So that means that f of 0 has to be 1. So now we plug f of 0 equals 1 into this equation, and we get something that we recognize as being f prime of 0. This is definitely like a tough question for sure, right? It's question 10. I told you it was challenging. This is definitely on the harder end of things. Yeah, Gurpratap, put a request in for that. Angelo marked especially like question 2 and was like really weird about what he thought was messy. Like there was stuff there that, because I've been looking at a couple of people and I'm like, this isn't messy at all. And he deducted marks for it. So just bug Aziz about it and see what he says. Ahmed, what's, are you just upset that it's a hard question? Yeah, I don't know what to tell you. Like as you problem solve more, listen, here's the thing. I largely blame bad high school systems, but if you guys had been learning how to do good math from the beginning, I think you all like this stuff wouldn't be weird to you. Like, no, it's just a matter of practice. This is a hard question. I don't expect everybody to get this, right? So for sure, this is a hard question. And if it doesn't make sense to you right away, there's no expectation that that would be true. But, you know, like if you ever lift or play an instrument or play a sport at all, again, you don't want to do just what you're comfortable with, right? Sometimes you got to push yourself to be a little bit uncomfortable and do stuff that's a little bit harder. And that is, that's the sort of thing that this is supposed to achieve, right? It's supposed to just make it a little bit tougher. How do we know f of h is f prime of 0? It's not that f of h is f prime, it's that 1 is f prime of 0. So this thing right here is f of 0, right? So then I put that into this thing. So are you asking how do I know that that's f prime of 0? Right. So what's the limit definition of f prime of 0? That's the limit as h goes to 0, f of h minus f of 0 divided by h, right? Like if you just plug everything into the limit definition. That's a little bit messy. Let me. Right? So like it is f prime of 0, right? Yeah, it's one of these things where again, you had to like, you might not have jumped to it immediately, but hopefully you're like, oh, okay, that kind of looks like a derivative, right? It looks like a difference quotient, right? Because you divided by h and you got some f of h in the numerator. So it looks hopefully like a difference quotient, and it's supposed to kind of inspire you to think about it like that. So f of 0 can't be 0, because if f of 0 is 0, then f is the 0 function, and it can't be the 0 function because f prime of 0 is equal to 1. Does that make sense? Like there's a little bit of like logic going on there that you have to reason through. So you say, okay, well, what would happen if f of 0 was equal to 0? If f of 0 is equal to 0, then f is the 0 function. That's this thing I crossed out here. Let me uncross it out. Okay, so if f of 0 is equal to 0, we can show that f of x is equal to 0 for all x. So that means that f is constantly the 0 function. But if f is constantly the 0 function, then its derivative is also constantly the 0 function. And we're told at the beginning of the question that f prime of 0 is equal to 1, right? Namely, it's not equal to 0. So it can't be that f of 0 is 0. Otherwise, we would have that f prime of 0 had to be both 0 and 1 at the same time, and that's not possible. So we were able to conclude that f of 0 is equal to 1. Does that make sense? Maybe Rafid. All right. No, unfortunately, yeah. This is the only way for this question because these are the only tools that you have. Okay. Anyway, everyone, give me like 2 minutes really quick. And I'm just, is there some formula or something in the notes that reflects part 5 of the assignment? Let me take that up. A couple of people asked about part 5 and part 8 of the assignment. I'm going to go, when I come back, I'll answer that. And then I'm going to do 511 and 513 by request. Okay. So give me like 2 minutes. Oh, Devin, do you have to run? These are the same thing. Okay, so I think there's a video called the alternative definitions of the derivative, and I would check it because I go into, I think if I recall, go into detail in that video about like why these are the same thing, and I like draw a picture and everything. And where are the readings? Yeah, so it's the alternative definition video. Right? Okay, give me like a minute, 2 minutes, everyone, I'll be right back. Okay, I am back. So Rafid, which one was your assignment, or which question were you asking about? 8.1 is the graph on the upper right quadrant. Hold on, let me pull it up. Come on, Corcus, why are you so slow? 8.1 is the graph towards infinity. Are we, or if you mean the upper left quadrant? Well, upper right is g of x. Like it doesn't make sense. Yeah, but that's the upper. Oh, I see. You're saying in the upper right-hand quadrant of f of x. I see what you're saying. Yeah, I understand. No, that's asymptote at 0. Yeah, so it definitely does go through at 0. It's just, it gets very, very big. But yeah, it's going to infinity at 0. Yeah. Does that help? Cool. Right. Yeah, Davin, exactly. Yeah. Okay, cool. Now, for those of you here, let me just, the video, our office hours from last week, it's just, sometimes it's easier to compute things. Same with the alternative definition. So what I'd recommend that you do is try to compute the derivative of x squared using both definitions. Okay, so try doing, why is my, yeah, my Surface is really not keeping up here. There it is. Here, I'm going to try and fix this. But try computing the derivative of x squared using both definitions, and you'll see they're quite different. In the definition on the left-hand side, you'll factor. Factoring is going to be the main thing that you do. In the right-hand side, there's no factoring, but you have to expand a polynomial. And so all it does is give you a different way of computing the derivative. And sometimes having just more than one way of attacking a problem is really, really nice because it allows you to solve problems that you might not have been able to solve with the other way, right? If it's in the test, should we just say use dy dx something to directly get the answer or use limit laws? Connie, be more specific because I'm not quite certain what you mean by that. And hold on, I'm just going to unshare because I'm going to try and fix the internet on this thing. I don't know why it's being stupid. Nothing. I'm not. Wait, are you saying don't worry about it, or what? What do you mean no network? All right, there we go. I think I'm hardwired. Sweet, I am. Okay. Any ways to reduce writing? No, just like, and your goal isn't to reduce writing, right? Just remember, your goal is clarity. So if you think you can communicate something clearly with little writing, that's okay. If you need more writing, just include it, right? You have 24 hours to write the test. It usually doesn't take that long to include a couple of extra words. Even when we do tests in person, I usually say, just do it anyway. But yeah. Okay. All right. Now, in terms of assignment, where's my Surface screen? Why is it not? Okay, there it is. Why is it still? Right. This is not reacting. I'm moving the screen and it's not showing on my screen. Yeah, apparently nobody is happy about doing more math. It's weird that the tests that are supposed to say no. Okay, so here's the thing as well. Like I'm running into the same sort of thing. Like when you give students more time, I guess they tend to take more time. So for example, my 257 class, I give them tests that I normally would give and they could write it in 2 hours. And some of them are telling me that they're taking 10 hours to write it, right? Which is just, if you give students more time, they might use more time. It's just that theoretically it could be written in that short time period. But for those of you who need more time, you're free to take it, right? That's what I want you to do at the 24 hours. I don't want you to feel pressured like the time is a factor. So if it takes you longer because you're taking your time and you're thinking deeply about a problem, that's phenomenal. I love that. You shouldn't feel bad about that at all. That's exactly the sort of thing I'd want you to do, right? And I'd rather you spend 3 hours on it or 8 hours on it than be tempted to ask a friend or look up on Chegg or anything like that, right? So like any day of the week, I'll take that. That's what I'm saying. The goal of the 24-hour assignments was to try and take the pressure off of all of the students so that you guys didn't feel like either you needed to, cheat. And again, sometimes that happens anyway, right? It's not a time thing. Sometimes just life sucks and people are tempted to do that, whatever, right? I'm not going to judge anyone for that. But to try and being in a pandemic is already a stress multiplier, right? Your lives are crappy to begin with. So if we can throw you something that might make your life a little bit easier, that's kind of the goal there, right? Yeah, absolutely. Yeah. I think you're probably right there. And a lot of getting stuck, right? Like math is really about, one of the things that we really try to emphasize to our math students is it's okay to be stuck on a problem for hours. And because when you eventually get through it, you will have made huge gains, right? The gains of getting stuck on a problem and getting past it are really, really big. So Sylvia, I would just like Aziz has been really sick for the last week. He probably just hasn't been super on top of his email. Maybe just send him a reminder. Yeah, okay, so Ahmed, what I want to do first, I'm going to do 511 and 513. The only thing that I want to do first, though, because I know that some people are bugging me about the assignment, but I did cover the part 5 and part 8 in the office hours on Tuesday. So what I want to do first is just link them really quickly to the office hours. And then hopefully for all of you people asking about that question, you can take a look at those office hours, read it. And if it doesn't make sense, if we still have time at the end of class, or at the end of office hours, you can take a look at it. So, right here, let me just get you. Okay, so here. All right, so everyone, so for those of you especially asking about the assignment and questions 5 and questions 8. So on Tuesday, I was asked to do 5, 6, and 8 and to do questions like that. So I did do them in my office hours. Here is a link including to the timestamp where office hours actually began. So take a look at that. Try, fast forward if you have to. Oh, sure. Yeah, I might be able to do something like that. Or maybe let me put it in the blurb and I'll see if I can't put it in the blurb. And then look at that and give that a try. Let me try and do 511, 513, because I'm going to ask like really early in the class. So let me do those. And then if we have time, I'll try and do these again. But if not, that's probably a resource that you can use there in order to look at those questions. Okay, let me pull up 511, 513. Okay, I'm already there. 511, don't worry about 511 at all, Ahmed. So I've actually since taken it off the readings. You probably didn't notice, but I actually took it off the readings because it uses stuff that we are not doing this year, right? We're not doing horizontal asymptotes and that stuff. But for 513, yeah, so let's do 513 then. And again, hopefully, it's a little bit slow, but it's okay. So 513E. So this is find and classify the discontinuities, right? So find and classify discontinuities. Okay, and so this is kind of antiquated. I think it says log x, but I want it to be ln x here. There's a while when we used to teach the class as log being ln, but they're the same thing. So don't take log base 10. Let's use log base e. Okay, sure. Okay. So x is, if we want to look at the discontinuities, right? It's actually enough to look at the discontinuities of each of these functions separately, because the limit laws say that the product of continuous functions will be continuous. Okay. And so the converse of that statement is that this function will be discontinuous at a point if and only, or precisely when it's discontinuous at, or one of its functions is discontinuous at that point. Okay, so we want to look at where are these functions discontinuous. So let's start with x. Where is the function x discontinuous? Like where is it? Where does it fail to be continuous? Exactly. Yeah, nowhere. So at 0 though, Ahmed, right? F of 0 is 0, and the limit as x goes to 0 is also 0, right? So this function is everywhere continuous, right? So x is continuous everywhere. And what about, okay, yeah, exactly. And that's the next question. But a thing that will help as well, if you go back and you look at the continuous video, one of the things that I do in that video is I give you a list of functions that you can assume are continuous everywhere. And I'm pretty sure I say, polynomials, exponential functions, stuff like that. So that will definitely help if you go and you look at that, okay? Yeah, and so now where is ln x? Where does that one not continuous? Or like maybe we should say, where's the only place we could potentially run into trouble? Does anyone know? Okay, yeah, so x can't be negative and it can't be 0. So that restricts our domain immediately, right? So Devin, you're absolutely correct. X has to be strictly positive, right? But yeah, if you want to think about it like that, like x being negative just isn't allowed. It is allowed for the x in front of the ln part, but we're not allowed to put it in the ln. So we probably just throw it away from our definition. The only thing that can really, so our domain, first of all, as a result of this, so the x must be positive, right? Okay, so this immediately tells us that the domain of this function is 0, infinity, right? Right, okay, sure. Yeah, that's absolutely true, Dan. Exactly. And that's why ln x can't be 0 or negative for the same reason. Jeremiah, like x is continuous everywhere because the limit as x approaches a of x is always equal to a. Right? And that's the same thing as saying it's continuous everywhere, right? I can just evaluate the limit by plugging the limit point in. Okay, now, for this reason, if its domain is 0, infinity, I would actually say, and I hope the answers don't disagree with me here, this function is continuous on 0, infinity, right? There's no point at which ln x is actually discontinuous. The only point you might have a case for is you could say that the function is not continuous at 0 because the limit as you approach 0 from the right is equal to negative infinity. But strictly speaking, on this domain, this function is everywhere continuous. It has no discontinuities because neither of its functions have any discontinuities. Is that okay? And if you graph this, remember a discontinuity of a function is basically a hole in its graph or some place where it jumps. And if you graph this function, you shouldn't see any holes or any jumps, right? Yeah, so yeah, and whenever you ask about continuities, it's always about on the domain of f of x. And in this case, yeah, exactly the same. The domain is 0 to infinity. So those are the only places we're going to look for discontinuities. So for like part A of this exercise, I took the two functions that were dividing by each other and separated them and set the limits. Sure, yeah. I mean, but what do you mean? So did you, so basically what you want to do, so you've got, so for part A, right, you've got x cubed minus 3x divided by x minus 3. Okay, this one. So the only potential place of issue is going to be, right, that like the numerator is everywhere continuous. The only possible issue is where the denominator is 0, right? Because you're not allowed to divide by 0. And so your only possible point of discontinuity here is x equals 3. Does that make sense, Ahmed? Like, is that what you did? Or, right? Because here I don't want you to think of x minus 3 as being the function. I want you to think about this as 1 over x minus 3 times x cubed minus 3x, right? And this thing is discontinuous at 3. Yeah, because remember, you're not allowed to divide by 0. So that's why we have to be a little bit tricky. Like, you don't want to just think of the denominator as being x minus 3, because x minus 3 is fine at 0, right? But 1 over x minus 3 is not allowed. So yeah, x equals 3 is going to be the only issue there. But this one's actually going to be removable because it turns out, oh, sorry, this should, is it x cubed? Oh, it is x cubed. So yeah, what's going to happen? X squared minus 3 divided by x minus 3. Yeah, it's the only discontinuity. And it looks like it's going to be essential, actually. Yeah. All right. So you're just looking for where the function is basically badly behaved, right? Like that's, and I say badly behaved because you're dividing by 0, because there's like a jump in it, right? Especially with piecewise functions, you tend to see those jumps. The absolute value will sometimes give you jumps as well. You're looking for places where there are holes, right? So just places where the function, you can't kind of draw it without picking your pen up from the paper, right? That's the way some people have described it. A function is continuous everywhere if you can draw it without picking your pen up from the paper. And so discontinuities will occur wherever you have to pick your pen up, in order to continue drawing it. Yeah, exactly. Yeah, yeah. So the functions that you can write down in general will be continuous, right? Like there are functions that have lots of discontinuities, but most of the ones that you know how to write down will be mostly continuous everywhere. We really have to like kind of fudge the functions in order to even come up with stuff that's discontinuous, right? And Avi, yes, because e to the e is continuous, so it means you can take the limit inside, right? That's the important thing about that thing. Yeah, sure. I mean, yeah, try it again and see what you get. And then remember, you can totally post things on Piazza, and we're happy to check your work on Piazza. And because it's not an exercise problem, you can just post it publicly. You don't even have to do it privately. Rafid, sorry, I'm just getting to your message now. Able to determine. We weren't able to determine what happens outside the graph. So am I only able to? What do you mean? Rafid, so you're right, you don't know what's happening outside of the graphs of those functions, but I don't know what you mean only determine one. So if you can, oh yeah, don't worry, if there are discontinuities outside of the graph, don't worry about it. So just tell me the discontinuities that you can see on the graph. Does that make sense? And Ahmed, yeah, hopefully that helped a bit. So please try those, and then if there are any questions at all, don't hesitate to throw on Piazza. Avi, so if the limit doesn't exist, then the whole thing doesn't exist. It depends on what you mean. So you should have seen in the writing assignment that it's possible for the inner limit to not exist, but for the whole limit to exist, right? So you have to be a little bit more precise about what you're asking there, because I suspect that's not what you're asking, but I don't want to give you the wrong answer because I'm misunderstanding what you're asking. Or are you asking like if a one-sided limit doesn't exist, does the whole limit not exist? Like, is that what you're asking? No, it is possible for that limit to still exist. Well, if it does, like, right, okay, so yeah, it's possible for the, here, let me give you an example. So let's take the function. All right, well, no, we can do better than that. Okay, so what is this limit? Damn, I don't like that one either. Yeah, okay, the limit as x approaches 0 from the left of 1 over x. So this doesn't exist, right? Because it's like 1 divided by 0. But effectively, this number is getting really big and negative. So there's a sense in which this thing is going to negative infinity. It still doesn't exist, right? But the number is going to negative infinity, right? Because the number is getting really, really big, but really, really negative. So now if I said, okay, so what is the limit as x goes to 0 from the left of e to the 1 over x, right? Well, this still turns out, right? Because this thing goes to negative infinity, this whole limit is actually equal to 0. Right? And plot this and see that it's true. So the reason for that is this thing is going to negative infinity. And when the exponent of e goes to negative infinity, the whole function goes to 0. No. It would be like e to the negative infinity. Okay, I don't want you to write this down. Never, you're not allowed to write this down ever. Okay, but I just want to do this to illustrate to you like how you should think about it. So does that make sense? And that is 0. Okay, the thing that you're not allowed to do, you're not allowed to write this down, okay? Infinity is not a number. You're not allowed to plug like infinity into functions. But if you want to write this down as an aid for you to understand what's happening, I'm okay with that. But try not to write this down because the markers will for sure deduct marks for this, because that is not legal. You are not allowed to plug infinity into a function, right? And Jeremiah, yes, it's kind of for the assignment. Right, yeah, it's the same sort of idea, yeah. Though, of course, in that case, like we don't actually get to do 1 over e to the infinity, but it's the same sort of idea. Yeah, it is the same sort of idea. So Abby, does that make sense? Do you see how, like, so this limit doesn't exist, but nonetheless, the whole limit in a much larger context does exist for this reason. Now, that's not a guarantee, right? This limit could fail to exist and the whole limit could fail to exist. But just because the inner limit doesn't exist doesn't mean that the whole function fails to exist. For questions of the assignment, do we always plug the x? Depends on what you mean, Jeremiah. Like, again, if you know your function is continuous, you can plug in the x. If you don't know it's continuous, you can't do that, right? You have to do some more limit stuff. What if we first put e to the limit fx? Okay, so here's the other trouble you run into. The exponential, so if you're doing the limit as x approaches c of e to the f of x, right? And you want to be able to take the limit inside, e has to be continuous at the limit point. Okay. Yeah. So the outer function has to be continuous at whatever the inner function limits to. So if the inner function's limit doesn't exist, you actually can't take the limit inside in that case. So Abby, does that make sense? Right? You're only allowed to take the limit inside if you know that the outer function is continuous at whatever the inner function limits to. That's the only time you're allowed to do that. Yeah. So if the inner function doesn't exist, you actually just kind of have to do it from scratch. Saeem, sorry, I keep missing your messages. Can we only bring the limit into the composite when the whole function exists, or the outer one exists or the inner exists? Right. So the rule is, so maybe I kind of answered your question here, right? So the limit as x goes to c, let's not do this with e now, let's just do this with two generic functions like this, is equal to f times the limit as x approaches c g of x. If f is continuous at this number. Okay, so this number has to exist and f has to be continuous there, and then you're allowed to plug the number in. Or then you're allowed to take the limit inside. So, Saeem, does that also answer your question from before? The outer, yes, the outer must exist at the inner function limit, and it must be continuous. Okay, that's the other thing. I want you to include that word. The outer function must be continuous at the inner function limit. Okay, and Gerber-Tapp, so for continuity, remember the definition f is continuous at c if the limit as x approaches c, f of x equals f of c. Okay, exactly. No holes, no jumps, no, and exactly. So Gerber-Tapp, what you need to do is you compute this first of all, and then you compute this, and you check if they're equal. And if those two things are equal, you're continuous. And if they're not equal, you're not continuous. Does that make sense? No problem, Davin. Have a good night. I'll see you next week. No problem, Jeremiah. Gerber-Tapp, does this make sense? So if it was approaching 2, you have to find f of 2 first. Yeah, exactly. So if we were doing the limit as x approaches 2 f of x, for it to be continuous, it would have to be f of 2. Now, usually this is the easy part, right? Like you can just kind of plug the number in and hopefully you just get a number out, but you figure out what that number is, and then you compute the limit. And if you get the same answer, your function is continuous. But don't forget, like I was mentioning, actually, I don't remember who, maybe I was mentioning it to Ahmed. I've given you a list of functions you're allowed to assume are continuous. So make sure you go back and you look at that video. And, you know, again, I say polynomials are continuous, exponentials are continuous, that sort of thing. You're allowed to use that information, right? Like you don't have to do this from scratch every single time. And maybe you can save yourself some trouble with that. Okay, see you, Dad. Is looking off? Oh, it's fixed. Look at that, right? It's fixed. Also, can the limit of f of x be written as Avi? Yes, but you have to be careful about the direction. Okay, so that is true. What you've written is absolutely true. But if you need to compute one-sided limits, you have to be more careful, okay? So if you don't need to worry about one-sided limits, you're totally fine. But if you do need to do, okay. It's just dirty. I'm sure it's just dirty. Yeah, as long as it's two-sided, it's fine. When it's one-sided, I want you to be a little bit more careful about it, right? Think about like x approaching 1. What might that look like if I'm approaching from the right? 1.1, 1.01, 1.001, 1.0001, something like this, right? X, yeah, see you, Brandon. But then when you put negative x in front of all these things, what are you doing? Right? So x is approaching -1, but notice that it's approaching now from the left. See you, Simon. Right? So that's what I'm saying. You have to be careful about the one-sided limits there, is that it does flip, right? Like approaching from the right becomes approaching -1 from the left. For 7, the function f of 2 is just, here, let me just pull that back up again quick. Where the hell is it? Oh, there it is. And I closed it. For 7, f of -2. Gerpertap, that's correct. That is the value of f of -2. Right, f is not continuous at that point. You're absolutely right. So for, but for 7, you're saying, not for 6, right? So for 7, yeah, you're fine, right? You just need, f is the inner function. You just need that its limit exists. So you're right, f is not continuous at -2. But what I wrote down here, not there. What I wrote down here does not require that the inner function be continuous, right? It only requires that the limit of the inner function exists. And this is obviously confusing because in question 7, these are backwards, right? These are the other way around. Does that make sense? So you notice here, it doesn't say anything about f being continuous. It just says that the limit of the inner function f has to exist. And in that case, you're right, it's not continuous, but the limit does exist. Does that make sense? And I think you're on the right path. Well, it's exactly this. The yellow bubble here is exactly the right thing to do. Like you have it. You're just about there. Actually, this one's a little bit more complicated because the problem is that the limit of the inner function is 0, but g is not continuous at 0, right? That's the problem. So actually you can't. So you're going to have to do this as one-sided limits. The same way, you remember in the writing assignment and in the pool questions from week 1, how we just had to look at the limits as we approached from the left and right. So what you're going to have to do here. Okay, so I want you to take the limit as you approach -2 from the left and the limit as you approach -2 from the right. Yes, Ariana, yeah. In fact, it is not going to cover derivatives, and 2 of the 3 questions will be expected value and probability. Yeah, Gerber tap, exactly. That's the right way of doing it. So just, yeah, take along that. I mean, we haven't tested that stuff, right? So I'm gonna post an announcement tomorrow though that will say that very clearly. So you'll know for sure. No problem. Avi, so for 5, 5 is tricky. You have to do the one-sided limits as well. Avi, like you can't, I talk about it a little bit more in that video as well, the office hours from Tuesday. So even though I kind of start by talking about how we'd put the limit inside the E, the problem is that the f of x the limit there actually doesn't exist. So I recommend taking the one-sided limits. So for part 5, take the limit as x approaches 0 from the left and take it as you approach 0 from the right and see if that limit exists. Does that make sense? Yeah. No problem. And remember, right, you can throw stuff on Piazza. We're happy to help you there. I don't teach tomorrow, so I'll probably be on Piazza a little bit more. But yeah, work on it, throw some problems up. Happy to answer stuff on Piazza. Okay, but I think we probably have to run because it's 7:10 now. Absolutely, Ariana, thank you. Everyone else as well, have a good weekend. Work hard on your assignment and stuff. Like I said, I'm going to post some stuff tomorrow about the test. Okay, but I'm going to take off now. Have a good night, everyone. See you later.